Good afternoon. Thank you for joining us today. This is our fourth Events and Topics in Bioenergy. We are a seminar and site visit series sponsored by the Photosynthetic Antenna Research Center, PARC, and also by ICARES, the International Center for Advanced Renewable Energy and Sustainability. Today I'd like to welcome Dr. David Peters from the Department of Mechanical Engineering and Materials Science. He is the McDonnell Douglas Professor of Engineering and also Director of Graduate Studies. He is the Director of the Center for Computational Mechanics at WashU, and he also is the Associate Director of the Georgia Tech Washington University Center for Excellence for Rotor Technology. He's also an adjunct at Georgia Tech. So I'd like you to please join me in welcoming David Peters.
All right, we're going to give an overview today about wind energy systems, where wind energy fits into the total energy picture, some of the technology and engineering and physics that's behind it. We teach this as a course. In fact, the course this coming spring, we have a course in wind energy systems. Today's lecture is sort of like the introductory lecture to that course, only a little change for you all, but that's pretty much the way it's going to work today. So we have some prerequisites for the course, but today all you need is an interest in wind energy, I think, for a prerequisite today. If you're interested in a text, we use Wind Energy Explained. It's also the one of my good friends, Pat Moriarty, is head of the National Renewable Energy Laboratory in New Mexico, and he teaches from this book when he teaches wind energy systems at the University of New Mexico. We don't have any grading here today. There'll be no exams or questions at the end, but you can ask questions at the end. And hopefully you may have some questions that I can answer, or at least send you to the right place. And feel free to contact me, email me. You can find my website at Washington U if you wanted to talk to me about it. Well, let's talk first of all about the taxonomy of wind turbines. What do they look like? What are their parts? And then what the current market is for it. We're going to talk mainly today about horizontal axis wind turbines. And that means wind turbines that are spinning around like this with these big blades. Now there's also vertical axis wind turbines, where the blades go around in a circle, and they're very important for smaller applications, third world applications, maybe out at your farm. But we're talking about world energy, U.S. energy needs today, and for those we're going to see why it's usually the horizontal axis wind turbines are the most common. These big blades that go around are wings. They're just like the wings of an airplane. And just like the wings of an airplane lift the airplane and hold it up against gravity, these wings that go around, the lift on them turns them. It pulls them. And so the wind turns the wind turbine around and can turn a generator that can do work that needs to be done. The word wind turbine sort of evolves from other turbines. Originally there were water turbines. Hydroelectric plants. Water comes through and hits blades and spins the blades around to make electricity. They're steam turbines. If you have biofuels and you're burning them, you boil water and make steam. That steam can turn a turbine to make energy. And so wind turbine is the same idea. Like gas turbine, you might burn fossil fuels to do that, but here you're going to use the wind itself. Will blow on these huge blades and begin to turn them around to make the energy that you need. Now there's two kinds of these horizontal axis wind turbines. The one kind is upwind, and that is the blades in the turbine are pointing the direction the wind is coming from. So the wind first hits the blades and then goes on past the tower. The other kind is a downwind turbine, and there the rotor is downwind, the wind comes this way. Now advantage of downwind is you always want to be lined up with the wind. Wind is changing direction all the time, and you want to line up with it. When your wind turbine is downwind, it's sort of like its own weather vane, and so it can sort of match the wind. When you have an upwind turbine, you have to have a big yaw motor in here to turn it. You have to always figure out where the wind's coming from and change it. But the disadvantage when you go downwind is that the wind hits this nacelle and hits this tower and makes turbulence and eddies, and they come off and hit your blades. And then your blades will start to vibrate more. And so usually most of the large wind turbines today are upwind horizontal axis because of these vibration issues. And then they have some sort of control. And we'll sort of look at that as as we go on here. All right. The current market, almost all wind turbines you would buy, for large-scale applications would be horizontal axis wind turbines with 2 or 3 blades. Now, with 3-bladed machines slightly favored. Now, in the course we talk a lot about the number of blades and why, but today I'll just give you a short answer. In general, more blades is more efficient and lower vibration. So you would like to have a lot of blades, but more blades is more complexity, more moving parts, more expensive. And so really you're driven down to few blades. But if you only have 2, then you don't have symmetry. You don't have polar symmetry. When the blades are in this position, you have one moment of inertia this way and a very small one this way, and then when they get to this position, it's opposite. Once you have 3 or more, you have polar symmetry, the vibrations are canceled out, and so people just pretty much gravitate to 3 blades, or sometimes 2. But 2 or 3 blades are going to be the most common. There are wind turbines today up to 7 megawatts. How much is a megawatt? Well, that's like 100,000 60-watt light bulbs, roughly. All right, we'll look later on how that fits, and there's some very large wind turbines operating today. The size you can buy a 1.5 megawatt turbine. You can go right now and buy one from GE for a few $1 million. Have it shipped right out here to WashU if you would like to have it. Now let's look at the components, okay, of our wind turbine system. There's the rotor itself. This is just sort of a block schematic diagram. This is the rotor. These big wings are going to be here. That's going to be turned. There has to be a hub that connects those blades into some sort of a shaft. And the shaft has to go through some gears, a drivetrain, to get to a generator. The wind turbine is turning very slowly. The tip of the turbine is maybe only moving at 1/6 of the wind speed. It may take it several seconds to make an entire revolution, but you want to generate electricity at 60 cycles per second. So you need something to go high, so you have to have a gearbox that's going to take you from low speed to high speed. Then you go into your generator that generate the electricity. Anything you can put down here, you do. You don't want to put stuff up here you don't have to, because the whole tower has to be designed to carry that weight and all those loads. So you may have a lot of your electrical stuff down here, but electricity's got to be made up here. It's the electrons that are going to go down some wires before you get ready to send them to your electrical grid. I mentioned you have to be able to point at the wind. So you need some sort of a yaw system, a large yaw motor in there that can measure where the wind's coming from and turn. And it's not easy to do that. If you've ever done this physics experiment where you took a big bicycle wheel and started to spin it and then tried to move the bicycle wheel, it's got angular momentum that doesn't want to change, and you try to do it, it's hard to do. This big wind turbine is like a big gyroscope. Although it's moving slowly, it still has angular momentum. And so it's not easy to turn it, and you can't turn it just as fast as you'd like. You have to turn it slowly, all right, to keep the loads down. That could be a problem if the wind's changing directions quickly. But that's usually this yaw motor, and how fast you have to yaw this machine designs everything up here. The weight of the system, how big the tower has to be. So everything is about that. And then you need some controller, right? We need computers to do this. You need some controllers to tell you, is it time to yaw the wind turbine? How far should we yaw it? Is it time to shut down if the wind's too high? Or is it time to start up? So you need some computer control in there to control this. You don't want to have a person sitting at this wind turbine. We're talking about wind turbine farms down in Texas, with hundreds of these 2 megawatt wind turbines as far as the eye can see. And you may have a computer control room back somewhere, but you just can't individually throttle each one. There has to be a control system that knows when to shut down. It has to measure if there's a problem in the gearbox, right? If you feel some extra vibrations you didn't normally feel, you don't want to wait for the gearbox to break, because that's going to take you a long time and a lot of money to fix that. You want to shut it down now so you can do the right amount of maintenance. From aerodynamic considerations, almost all wind turbines have a circular cross-section tower. It's easy to manufacture, and from an aerodynamic point of view, it has the lowest drag, so you're going to see that in almost all towers that you will see. Here's more of a, not just a schematic drawing, more of a real figure than of what we're talking about with a wind turbine. You have, first of all, your rotor with these wings on it, these large wings, 2 or 3. The wind's coming from this direction. The height of this tower, of course, has to be bigger than half the rotor diameter, because this has to be off the ground. Here you have your gearbox we talked about, your generator, and then it's covered with a nacelle. This is an aerodynamic fairing that keeps everything. You don't want a lot of wind drag on this because that puts more loads into the tower. You get plenty of lift from these blades to try to bend the tower. Your yaw control system we mentioned, and now here's something new. You need a brake, right? Because sometimes you have to stop this thing. Maybe the gearbox fails or something goes wrong. You don't want this to spin out of control. So you have to be able to slow it down, or maybe there's a large thunderstorm coming. You want to stop this thing, so there has to be a brake. You want to be able to throttle this wind turbine to take what energy is available. Sometimes there's low wind, sometimes there's high wind, sometimes there's more energy than you can even take. So most of the blades are made so they can change pitch. Okay, so you can throttle back the wind turbine to get just the optimum amount of power out of the air you possibly can. We'll talk in a little bit about what the optimum is. So these are part of the parts. You have your support pad down here, your foundation below the ground, where you have to support it, and then all of the electrical stuff, your power has to go to your substation, your control panel, everything that has to be down here. Okay. Inside that nacelle, if you look a little bit closer, here's our hub, our main shaft, our gearbox, the brake, the generator, right? This is the part that we're talking about, and this whole thing is called the nacelle. I'll show you some pictures of some nacelles. They're larger than you might think. Now, how has wind energy grown? Here's to 2009, and I'll fill you in for the last couple of years what's happened. So here's the years we're talking about here, coming up to 2 years ago. Here's how much was added each year, all right, in terms of megawatts. How many megawatts of machines were added each year, and this is the total then. So at this point, we were just first getting into the first 240 megawatts. Now, a lot began to be added right in here because there were tax credits. California especially gave tax credits to people to build wind turbines. And people build huge wind farms. Sometimes they wouldn't even run the wind turbines. They just build the farms to get the tax credits. And right about 86 or so, the tax credits ran out. And then, wow, you're down to 1 new megawatt was added in the 1996. You're pretty much flat here what happened. But the price of energy began to go up. Oil became more scarce. You know, we had 911 that came in here. We began to worry about energy. And all of a sudden, things began wrapping up. So by 2009, we had 32,000 megawatts. That's 32 gigawatts of installed wind power. Now we have about 40,000 right now in the United States today. And it's ramping up quickly. If you like charts and bar charts, this is that same information. But on a bar chart, the red is how much we added each year from those same years up to 2009, and then the green is the total. So you can see we have been ramping up very, very fast. Back a few years ago, we were talking about maybe 1% of the U.S. electrical power was coming from wind. Now it's up to about 3%, and it's going up fast. Going up fast. If you put that on another kind of chart like this, just kind of put a fairing through it, just maybe to see what's happening, and you begin to extrapolate this out. You say, can it keep on going? How high can it go? Where is it going to go? And people have a pretty good idea of how far this can go, where it can finally end. And basically the bottom line is, there's the goal by 2030, we probably could be doing 20% of the energy in the United States from wind. By 2050, we might get to 30%. It's doubtful we'll ever get more than that. There's just not enough wind here. You say, well, why worry about wind? Because that's a huge amount, 30% of your total energy from a completely renewable resource. But it's not the total answer. And of course, the numbers depend on a lot of things. We'll talk about some of those, whether that's going to be feasible or not in the United States, in the world, or wherever. All right, but definitely wind is going to be a big player. I was in Texas, a friend of mine, Andy Swift, one of my former PhD students here who worked on wind turbines, went on to be Dean of Engineering at University of Texas, El Paso, and he's now at Texas Tech, head of their wind program. The state of Texas predicts that within 10 years, wind energy will be more money in the state of Texas than the airline industry. It will be a larger industry than the airline industry in terms of the amount of money. And they're building infrastructure, they're building wind turbine power lines to carry the power, and they've got a lot of wind to do that with. So that's really where we're going to be headed. Let's look at kind of a history. What went on in the past and with wind turbines? Where is it that we are now? What's going to happen? If you try to go back to the first time people ever harnessed the wind, around 400 AD, there's references to Buddhist prayer wheels driven by the wind. You know how this works? You write a prayer out on a little wheel, and every time the wheel spins around, that prayer goes up to heaven. So you'd put these prayers on wheels, and you'd spin them, and somebody figured out they could make a little windmill, and the wind could spin the wheel. You could just sit back there and go take a nap, and the prayers are just going around and around. So people had already seen that, you know, wind could turn something, wind could do something. From about the 13th century to the 19th century was really the golden age of windmills in Western Europe. There were about 10,000 windmills in England, 18,000 in Germany, 9,000 in Holland. If you had everything up all over Europe, probably 50,000 windmills at that time. In the United States, about 1850 to 1930 was our heyday of windmills. The small windmills in the Midwest around here that were on farms, you can still see them if you drive through Kansas and Nebraska and Missouri. They mainly pumped water. The windmills pumped water to fill tanks to feed cattle so the cattle could drink. And they were all set up with a vane, and when the wind speed got too high, a flyball governor said the RPM's too much, and it just took the vane that's turning the windmill and just rotated at 90 degrees. Now the windmill just went horizontal to the wind, just parallel with it, and just sat there. Or when the water tank got full of water, there'd be a little bobber in the water tank. When it got high, remember it was supposed to happen at what's that? The reservoir in Missouri, Johnson shut-ins, right? They had one of those on. Yeah, it was supposed to happen there, and it didn't. But then we shut off the wind turbine too. And then when the water would go down in the tank, or the wind would go down, it would flop back again. So there were just thousands and thousands of these around the country. 1933, Krasnovsky in Russia built a 100 kilowatt machine. It's not very big by today's standard, but it was way beyond what other people had thought in the Russian Crimea. I probably should go back to the windmills in Europe and Holland too. It turns out the Dutch figured out some very important things about wind turbine design. One of the things they figured out that people know in airplanes today is when you have a wing, you should put the center of mass 1/4 of the way from the front of the wing to the back. And that's, they learned to do that, and they learned to put the center there. There was a time, it's a great story, when they discovered that the wings shouldn't just be straight, you should twist them. So they cut into the wind more near the root and then less as you went out. And there's a story in Holland when they first did these big wooden windmills that did a lot of grinding of the grain. When they first tried that and put the nonlinear twist, it developed so much more power it tore up the entire wooden transmission and gears. So they just weren't, they knew it would be better, they had no idea how much better. They learned to make good airfoils to fare them, so there was a lot of things were learned by trial and error. But when he got down to Krasnovsky, he really began to use aerodynamic technology and built a fairly large windmill in the Crimea. 1973, that's when the oil energy crisis came and really inspired new interest in alternative energy sources. From 74 to 80, there was a federal large wind turbine program that was developed. We got a lot of funding here at Washington University for that. We built a 25-foot diameter wind turbine that operated out at Tyson Research Center. You know, they have a lot of salamanders and wolves, but they let us clear a ridge out there. We built this wind turbine, we ran it for 20 years out there. Okay, I remember when we sent in our report of all our expenses to the Department of Energy. They sent it back because we had charged for mouse traps and tick spray. And they said, "What are you doing, Jordan? You can't charge for..." I said, "Yeah, we're out in Tyson. The mice are chewing through our Apple computer cables. Man, there's ticks everywhere, you know." So they let us charge mouse traps and tick spray to the Department of Energy to do that. Okay. In 1976, the U.S. Energy Research and Development Administration, ERDA, really got interested in small wind turbines, and NASA got interested in big wind turbines. They built their Mod O, a big 100 kilowatt machine. And But then from 81 to 2007, there was sort of this boom-bust era where things just went up and down and up and down. From 81 to 93, we had in California where more than 12,000 units were installed, but then when the tax credits went away in 1985 and 86, they just began to go down. But the Europeans were going strong. In 1991, the first commercial offshore wind farm in Denmark. And these are where you put the wind turbines out in the ocean on pilings that go down below because the wind is really strong out there, okay, to begin to do that. In 1996, Kennebec Wind Power, which was our largest wind power place at that time, declared bankruptcy. And its assets were sold to Enron and then acquired by GE Wind. And you know what happened to Enron, but GE Wind is still very strong today. And they're one of probably the most successful U.S. wind manufacturer. They're selling these 1.5 megawatt machines. In fact, I'm doing some work with Mesa Lands Community College in Tucumcari, New Mexico. And it's a very economically depressed area, but they're training people at a junior college there to do wind turbine maintenance. And they're 300 or 400 graduates a year, and they're just going everywhere, they're being hired. Because they bought a 1.5 megawatt machine from GE with state money to help them develop, and they have it there, and the students can work with it and play with it. Washington University can play with it too. We can get data from there. We have this agreement with them. Okay. 1990 to 2000, there were just megawatts of installations in Europe, growing at about 20% a year. European manufacturers began to open factories in the United States. At that time, I have some students who worked down in Texas for one of those large wind turbine machines. In 2004, Germany put up this RE 5 megawatt machine. We'll show you some photos of it in a second. 126 meter diameter. It's now up to 7 megawatts. They've upgraded it by better transmissions, better blades. So at this point, it's now a 7 megawatt machine. In 2007, our Department of Energy announced a goal and program to further wind turbine development here, and we're in the midst of that right now. But if you kind of look at the world wind power capacity growth up to about 2008, this slide here sort of shows it. Here's the United States, Germany, Spain, China, India, and then the rest of the world. And you can see it's all growing. Back about 2005, we were a smaller percentage, but we're getting a bigger percentage now, but China's going to pass us. This China little thing, that's widening faster than we're widening. But right now, we have, if you look here, the largest, we have about 25 gigawatts installed power. Germany, Spain, China, and India, 2008. But China is passing us fast. So it's not just us, it's the whole world. They know about this, they know it's important. And it's going to be an important player in the future. I hesitate to show this next slide. It's kind of apples and oranges, and it's hard to make some sense out of it, but there's an important part I want to show. It's world energy resources. Now, it's hard to define what a resource is. Like, here's coal. Man, we got all this coal. We don't have much oil left, right? So you look at, there's not much oil left, but a lot of that coal is really hard to get to. Same way with the natural gas. There's a lot of natural gas hard to get to, and it's apples and oranges because nuclear, I mean, I don't know, is that how much nuclear stuff we have now? There's all the deuterium in the ocean, you know, that you could get, everything. But hydro, this is just how many dams are made. You can get a lot more. But renewables, which are right here, and I don't know why they didn't put hydro renewables. This is the main thing I want to get in on. If you look at renewables, you got wood, geothermal, and other. And again, geothermal could widen if you sunk more geothermal hole. But you can see wind is a pretty big hunk right now of all the available energy resources. Solar is a pretty tiny sliver, but could get huge, right? So that's why I said it's kind of hard to say what they call available resources. But it gives you a picture right now of wind. And the wind is a pretty important player at this time, being about 42% of all renewables at this time in terms of resources is from wind. Now, back in 2005, I said we had a smaller percentage. Back then, we only had about 15% of the capacity. Germany has much more. We have now passed Germany. We've passed Spain, but China is coming right behind us. Okay, and it won't be long before China will pass us up. And it all depends about how fast we go and how fast we develop wind energy, where all the wind energy farms go. You know, we have the congressional mandates that say you have to develop so much energy from renewables. Missouri has laws about that. But like Missouri really doesn't have much wind. There's like one tiny place up in northwest Missouri, maybe another one up in northeast corner where you might have enough wind. So for Missouri, we're going to have to buy wind energy from other states, I mean, to meet the mandates. It's just not here. And, but that doesn't mean we can't do that or do some kind of trades. In a Sun Sentinel article back in 2007, they quoted the Department of Energy as saying that the nation's wind power capacity increased by 27% in 2006, and that we had the fastest growing wind power capacity in the world in 2005 and 2006. And now China's passed us in terms of their rate of increase. But despite wind farms, that means a whole bunch of wind turbines together, now operating in 36 states. In 2007, there was just 1% of our power was from wind. Now today in 2011, it's 3% of our power, so it's triple. And it's going to go up. It's going to keep going up. Of course, the demand is going up. You know, so the pie you're getting a piece of is growing. So you have to grow faster than the pie grows, even to keep your percentage the same. 2008 to 2011, these last 3 years, is sort of the green energy era. The wind turbine booms have been all over the world, especially in Europe, US, India, China, Australia, and New Zealand. In the United States, unprecedented federal and state funds support wind turbine development. There's tax credits, research funding, development grants, loans, wind turbine technician training programs through community colleges, like I talked about at Mesa Lands Community College in Tucumcari. So by the end of 2010, we had 40,000 megawatts installed in the United States, which is 3% of our total energy. It could be 20% by 2030, could be 30% by 2050 if we keep along the same pace that we're going. And that's sort of, I think, the goals that the government spent. Wall Street Journal, here's another article. Wall Street Journal said the federal government through the Department of Energy has done a large role in shaping the clean energy sector, and they plan to put $40 billion into companies to work on clean technology during 2009. And the agency at that time allocated $13 billion to businesses who were developing electrical vehicles, batteries, wind turbines, solar panels, or whatever. In comparison, venture capital firms have at that time invested about $2.68 billion in clean energy. So the government's a big player here. The venture capital is going to be a larger player. Okay, where does this fit in? Let's just look at Missouri for an example. We say the United States has 40,000 megawatts of wind. How does that compare? Well, Labadie, our coal-fired power plant here in Missouri, is 2.4 megawatt machine. So that means the US wind is like 17 Labadies sitting around the country. Our Callaway nuclear plant is a 1.1 megawatt nuclear plant here in Missouri. So it's like we're talking about 38, 39, 40 Callaway plants. So it's a lot. Only 3% of the total in the United States, but it's still a lot of power, and it's going to make a significant impact today, and it's going to even make a more significant impact in the future. Now, if you look at how much it costs, because that's one of the big things, how much does it cost per installed kilowatt hour? How much does it cost to build a power plant? Because you got to pay that back. Missouri has this law, they can't charge us users for a power plant until after they build it, right? So that's really caused a problem. Back in the 70s, when interest rates were 18%, that's when they passed this law. And they were building Callaway at that time, and I remember the nuclear, that time Union Electric said, okay, we'll just borrow the money and we'll charge all you guys for it when we build the plant, and they're paying 18% interest on it. So it cost us more in the end, but that's the way the laws are written. So you're going to have to figure out how much is installed power cost and can it pay for itself. Coal is about $2,500 per installed max kilowatt. Nuclear is a little cheaper than that. Wind is more expensive than that. It's $3,500 for installed max kilowatt. So you have to trade off the environmental aspects against the pure cost aspects in terms of what's going to happen. Photovoltaic right now is about $6,000, but it's coming down. And the time could come when photovoltaic could be down cheap enough that it might make sense to build some large reactors. Some of the great wind turbine pioneers here I've shown here, there's Paul de la Cour of Denmark, Albert Betz of Germany did a lot of the theory on what makes the most efficient wind turbine possible. Ulrich Hutter in Germany, and this guy down here, Uriah Putnam. He is just an incredible guy, and you may have heard about what he did here in the United States. It's very important for historical interest. He was the first to demonstrate the development of large wind turbines, and he collaborated with Morgan Smith Company, and which was a public cert, and built a large wind turbine back in 1941. It was a 53-meter diameter wind turbine with 2 blades. It was 1.25 megawatts at that time, and it operated for 4 years and fed electricity into the public grid. In 1945, it was destroyed due to a fatigue failure. If you look at what people say about it, they say his results are remarkable when compared even with present-day turbines. In our textbook we have, it says the most significant early large turbine was the Smith-Putnam machine built on Grandpa's knob. Let me just go ahead, and this is what, based on 1937 prices, people estimated to build 10 1.5 megawatt units would cost them about $190 per kilowatt at that time. Other energy was $125 per kilowatt, and so they abandoned it, but it was really probably, this is a picture of that at that time. So just an incredible wind power machine. It was tilted like this because the wind is coming over this hill. Right? So basically the wind's coming up from this way. It's a downwind machine. So the wind's coming up over the hill, and so the wind turbine is tilted to catch that. It was 2-bladed teetering rotor like a lot of helicopter rotors are, and that was the major technology of the time. It was just an incredible thing. Okay, how much energy can you get out of the wind? Okay, what's really there? What's physics behind it? You're basically talking about, here's your wind turbine, has some big area, pi r squared. You got this big slug of air moving through it at some velocity u. How much power is in that air that's coming through your turbine? What exactly would be there? And if you do the math, you got the density, how many kilograms per cubic meter, you've got an area, you've got a velocity. You can compute how many cubic meters per second of air come through my wind turbine, or how many kilograms per second come through my wind turbine, basically. And then that's rho AU, the density of air times your area times the wind speed. Well, kinetic energy, you know, is 1/2 mv squared. So how much kinetic energy per second is coming through my wind turbine? It's how many kilograms per second times that thing. And so basically, if you work it all out and come down to the bottom line, basically your power density is 1/2 the density, your area times the velocity cubed. So wind power goes as velocity cubed. So if I have a wind site with 10 meters per second, and you have a wind site with 20 meters per second, you have 8 times the power that I do. And this is why you have to find a high wind location. You say, oh, you can't pick up much wind power when you're at 5 meters per second or 10 meters per second, because this goes to the cube. Now you can increase the area, make your wind turbine bigger, and that's very helpful. But you have got to get a place with high wind speed consistently, because the wind speed always isn't high all the time. And all these big power plants have 3 wind speeds that you have to, if you're going to look at one and think about getting one for your company, there's first of all the cut-in speed. There's some speed below that you can't generate any power at all. And so that, you don't even have enough power to turn the gearbox. So there's some speed, nothing happens below that. Then there's the rated speed. That's what you see on the brochures, right? How much power it generates. But that usually means the most wind it can take. It can't generate any more power than that. And then there's a cut-out speed, where the wind's gotten so high it can't do anymore. And so if you kind of look at a curve here of power versus wind speed, normally we have that cube. Normally it goes to cube. But you don't get anything until when you cut in. So you cut in here and finally you get some. But then as you start to go up, your losses get more and more. And finally, this is all the power you can take. You can't take anymore. and the wind goes faster, you've got to start throttling back and finally shut down. And so you've got to design a wind turbine so it matches the place you are. You don't want to have almost all the time your wind's out here and you can't even get it, or most of the time your wind's down here. And so each wind turbine really has to be designed for the place where it's going to be. Another way to throttle your wind turbine is to yaw it. To yaw it out of the wind, and there's some of the Europeans that do that. Well, let's look at some of the modern ones now, to maybe show some pictures of wind turbines. I talked about the European one. This is started out at 5 megawatt, it's now 7. Its cut-in speed is 3.5 meters per second. Nothing happens till then, right? Its rated wind speed is 13 meters per second. That's a high wind speed, but that's what it's rated for. The cut-out speed depends on the version. There's an offshore version they put out on the pilings. It cuts out at 30 meters per second. That's pretty hot. And there's an onshore version about 25. It's 126 meters in diameter, a height of 120 meters. So you can kind of picture what that is, right? So, and it runs for about 7 to 12 RPM. Once again, it takes quite a while for that thing to turn through one revolution. Here's a photo of them putting that thing up. All right, here's the tower. They got this crane, and there's a three-bladed machine. They're going to put that thing up at the top. Here's a picture of how it looks in offshore applications. But let me show you, this picture is my favorite. Here's after it's up. Now if you see that? Those are people up there standing on top of the nacelle, right? So this is the size that we're talking about. So we're talking about, if you look at the diameter of the wind turbine, we said was about 120 meters, but the height is more than half of that. By the time you get up the tip, you're like close to the height of the arch. This is the kind of wind turbines we're talking about, and talking about making huge farms of these. So this is a 7 megawatt machine. You put 100 into a farm, now you have 700 megawatts, all right, to do that. If you're kind of thinking, how big should a wind turbine be? Here's sort of the Washington Monument. If we were in St. Louis, we'd put an arch here. The arch is about up here at 190, it's about up here. So, 40 meter machines, 80, 120, they go from 50 kilowatts, 1,000 kilowatt to the megawatt, 5 megawatt up here, and then some of these bigger ones to 7 megawatt. This is the kind of size that we're talking about. Now, we talk about environmental things with wind turbines. They're not completely environmentally friendly. They kill birds and they kill bats. That's one of the bad things about it. Birds just fly right into them. Bats fly right into them. In Europe, there's been a lot of protests in Denmark and Holland both about bird strikes and bird kills. They're noisy. I mean, they're not noisy like a jet airplane, but they're going real slow and you just hear this. And they're ugly, people say. Now, to an engineer, I think they're pretty. Of course, when the Eiffel Tower first went up, people said it was ugly. And Parisians complained, and now they think it's beautiful. But still, there's those things. And so those are things people have to think about. Now, in South Texas, out in the desert, there's not many bird strikes, and it's not nearly that potential. But if you're in large metropolitan areas or offshore, there are those kind of things. Now, we talked about how much power you can get out. We have this power coming in through your wind turbine. To get the power out, I have to take energy out of the wind, so I have to slow the wind down. If I slow the wind down too much, then I got no wind coming through. Like you kill the goose that laid the golden egg. So I can't stop the wind, or I don't have any. So there's a maximum. It turns out the maximum power I can ever get out is to stop 1/3 of the wind speed. So if I've got, 100 mile an hour wind, I stop 33.3 of it, and I slow it down to 66.7. I can't get any more energy out than that. And that's an efficiency of 16/27, or about 59%. So you never get more than 59%, and really you're usually down maybe to 45% is what you get out. Then you lose power in the bearings, and the gearbox, and the generator. You have to convert this to 60 hertz. The frequency converter you lose. You have harmonic filters to get out you want a nice, pure, clean thing to send to hammer and UE. You have a transformer, because you got to keep the voltage up as you head. Finally, when you get down, you're probably never going to get more than 40% of that power coming in. So you got to plan for that when you're designing a wind turbine about how efficient it should be. Now, there's also maintenance, right? These things need to be up a long time, and you have to construct them, and you have to make sure they're maintained. Here's a typical cross-section of ER machine. You see it's a huge tower. You got to get that tower up. At this Mesa Lands Community College, they couldn't afford the maintenance agreement. They ran out of money. If their transmission fails, it's going to cost them $45,000 just to get a crane out, let alone to fix the transmission. Just to get a crane out that's that tall that can pull it off. All right, so you've got to really think about the maintenance and the long term of these things, okay, in terms of the things that come together. Here's an example of helicopter, one of the offshore machines coming down. Vestas is the company. I said that they have a plant in Texas, and I have some former students that's working there. This is one of the Vestas machines. So you can see helicopters, another way to bring in supplies, bring in the things you need. Some machines have an elevator in the tower, so you can go up in an elevator, or some kind of a winch system to bring supplies up, because you need to do repairs and maintenance and things. So this is all part of doing that. There's a wonderful movie out called Harness to the Wind. You can find it on YouTube, probably. There's a lot of rock climbers that are now making money by repairing wind turbines. And they rappel down and fix the blades. Because a bird strike, you get a big hole in the fiberglass. And so they rappel down with their little fiberglass repair kits and put the stuff in. And they say that they do that about two months a year, and that can fund their rock climbing for the other 10 months a year. That's how they do things. So, but yeah, so you have you see a lot of people doing that. This is the one in the Mesa Lands Community College, one of those kind with this. Inside of here is a winch system that you can get things to go up. Now, the last thing I'll talk about here is air density and wind turbine height. Why are we getting these wind turbines so high? And the answer is, when you go up in altitude, temperature goes down. So that makes the density of air basically get heavier. But because you're going up altitude, also the density goes down and this part wins. So as you go up in altitude, there's less kilograms, but there's more wind. And wind, remember, goes as the cube. Wind power goes as the cube of the velocity. So the higher you can get your wind speed. Now wind speed, of course, is variable. It's oscillating all over the place. But if you look at a plot versus altitude, here's your horizontal wind speed as a function of altitude. Okay? As you go up, the wind speed gets higher and higher and higher. And if you can get up into here, you can get a lot more power. And this has made a lot of companies think about very high altitude wind turbines. And I'm doing some work right now for Base Load Inc. And this is their concept of a wind turbine at 20,000 feet that's tethered. It's on cables. It's flown like a kite. There's 4 70-foot diameter wind turbines, and they lift it too. So they're the lift and they generate the power, both. All right? And then the cable also serves as the power line. Now you say that's just completely impossible. I admit it's high risk, but they've already got the land in Oregon. They built the base. The FAA has cleared the airspace, because this has to be cleared FAA airspace, and they built a smaller prototype and have flown it. Okay, and there's a lot of other companies also looking at tethered. There was a whole conference out at Stanford last fall on high altitude tethered wind turbines. You can use a balloon to hold it up, or wings, just lots of ways to hold it up there. When a thunderstorm comes, you gotta winch it in. Or if the cable would break, this is like a helicopter basically. It can fly itself down. In fact, it flies itself up. An electrical generator is also an electrical motor. It can go either way. So first you start sending power into the generators, and they turn the rotors, and you fly up and you lift the cable. The higher you get in altitude, the more wind speed's coming. You start getting power from the wind, you need less electricity. Finally you reach an altitude where it's just flying like a kite. You don't need any electricity. Then you start flying it higher. Now it's got more power than it needs, and it's starting to pump energy down your cable back to the ground. So this is their plan. So it's high risk, but it's very interesting, and we've done several students have done some really interesting research. Let's kind of conclude here. Sustainable energy development is what this is all out, and I kind of use this definition here. Sustainable means development that meets the needs of the present without compromising the ability of future generations to meet their own needs. And wind energy is one of those. I mean, it's not carbon neutral. You have to build them. You have to make these, you have to make steel or aluminum. So you're creating, it's not, it costs energy and it costs resources to build wind turbines. But you're looking at it's a sustainable thing, right? It's a sustainable thing that can be used into the future. It looks now with the present way tax credits are set up and the way electric power is going, that we probably could have 25% of our energy by 2035, maybe 30% by 2050. These large diameter wind turbines over 100 meters have been successfully developed. They're operating right now offshore in wind turbine farms, even up to 5 megawatts and now 7 megawatts. Denmark now in 2005 did 20% of its electricity from wind, and it's up higher than that now. So it's definitely something that's possible to do. I said it's not free, right? If you look at all the green energy options, or just all the energy options, how much CO2 emissions, per kilowatt or whatever. Coal, of course, gives a lot. Natural gas gives a lot. But nuclear, hydro, biomass, solar, wind, they all have a cost because you have to build the plants. And so you're going to create CO2, you're going to create SO2, you're going to create NOx. So it's not 100% green, but it can help. Here's the wind farm in Nysted in southern Denmark, and it supplies 166 megawatts of electricity. And these offshore ones, the wind is very, you can count on the wind. Day in, day out, it comes in off. And so European countries are planning to add much more offshore wind capacity in the coming decade. We did our own wind turbine research. I told you back in the 1970s, ending in 2001. And we're involved not with our own wind turbine, but with the Mesa Lands Community College, getting data from them. So by 2030 to 2050, we could get 20% to 30% of our power. We have not done much offshore. They tried to get some offshore stuff in Massachusetts. There was a lot of public outcry against it because of the visual effect of that. But wind farms on land as well as offshore do offer considerable promise to get a lot of energy. Right now, our current predicted capabilities for modeling turbulence, wake, turbine-to-turbine interference, dynamic stall, we don't know everything. People don't know in these big wind turbine farms how much some of the turbines slow down the wind so that the ones behind them, are they parasites against those? So there's still a lot of research to be done. I'm going to switch to this. I'm going to dedicate this talk to Professor Kirko Nezzer, passed away in 2001. He really ran our wind turbine effort here. I was just a young professor. We're working for him back in the 1970s. He really saw the future of wind. He was very anti-nuclear person, and he lobbied very, very hard in the United States against nuclear energy. And he lived what he taught. He bicycled to work till he was about 93 years old. He bicycled here all the time. His house, I don't think he ever ran his furnace or air conditioner. He had so much insulation in there. It was amazing. And every time he came over to my house, he was always adjusting my furnace to make it more efficient. I had to readjust it when he left because I'm a pansy in terms of that. But, so anyway, I dedicate today's talk to him, and I'm happy to answer any questions or try to answer any questions you all might have. Yes?
You're talking about the current capacity we have in the U.S. and maybe I'm misunderstanding the terminology, but if not, is there a difference between our capacity and the amount we actually generate?
Yes, there is. So we have 40,000 megawatts capacity. Now, that would be if we had full wind at every site all the time. We could generate that all the time, but we can't.
So it's really
That's right. It's what's the same with the nuclear plants and the coal plants. You have a coal plant with a certain capacity. You don't run that all the time because you only need peak power on a 105-degree day in St. Louis and everybody's running their air conditioners. So you have to install a certain capacity, but you hardly ever run up at that installed capacity.
I
Yeah.
mean, on the whole, do you know what are the comparisons between Norwegian?
No, I don't know in terms of actual number of
Yeah, that's
joules
what I-
created. Yeah, I don't. That'd be very interesting. But this is one of the problems with wind energy and some of the others. We can give you power when the wind speed's high. Ameren UE, Ameren Missouri, Ameren Illinois, they need it when it's a 105-degree day in St. Louis. They don't, at nights when the wind speed's the highest, and they don't need it at night. And so part of the issue is storing this energy. How good are our batteries? Or can we pump water up to a tank? Or is there some way to do it? And that's part of the issue that makes wind energy more expensive. Because when we had our wind turbine out here at Tyson, Ameren UE was forced to buy our power. So we had an electric meter and we ran it backwards. You know, we run backwards, we just ran. They had to buy it, that was the law. But they didn't want it to, because we weren't giving it to them when they really needed it. Right? But to really have a global solution, you have to look at that. In Europe, it's better. With these offshore things, you know, they're more consistent wind. So you have it all the time. But yeah, energy storage is going to be a big issue. But of course, on the other hand, we're not pumping CO2 into the atmosphere all the time. So that's the other side. And if we could get, you know, ideally you would run your wind at full power all the time and you throttle back your coal. Right? So that, and there will never, since wind will never be more than 30% of the total anyway, you know, there's no time you would have too much wind to be used. So, but still it's an issue if you look locally, you know, in terms of different parts. Yes?
So what is WashU doing about research and storage options?
Yeah, I don't, we have some battery stuff going on, but not much, yeah.
Can you just summarize that question for the
Oh, yes, yeah. The summary is, what is Washington University doing in research in terms of energy storage options? And I don't know much at all. Maybe some of you know if something's going on in physics or in the ECE department. But we're just now getting back into the wind energy business. When Hohenemser passed away in 2001, that sort of dropped. We actually disassembled our wind turbine out at Tyson, you know, but now if there's more money available for research, maybe we should get a consortium together and try to do, or maybe, you know, the iCares program funds some things, and it could be that iCares is funding some energy storage ideas. Yes?
Actually, I have an online question from
Yes.
Bob Blankenship, which is, how closely can you place windmills and not have them affect the efficiency of other ones?
Yeah. This is a question we don't know the answer to yet. And my friend Andy Swift at Texas Tech, they are now building a research wind farm and try to answer that question. People are guessing 10 or 20 rotor diameters that they don't know. If you know, like in airports, if a big 747 lands, it creates these big vortices. 20 minutes later, a small plane can come by and hit one of those and gets turned over. So this wake behind things goes a long way and a long time. And it could very well be just a vibration issue as well as a power issue, but we don't know that answer yet. Yes?
So you asked about blade design. You mentioned that the 3 blade design is the most common, but that more blades are more efficient. What's the sweet spot in terms of number of blades and, you know, what angle it is between them? And also, what about materials design and what's being done?
Yeah, the question was about blade design. For the number of blades, I mean, I think 3 is it. I think 3 is going to be optimum. Even though aerodynamically you could get more efficient, that's a very small amount because we can't get more than 59% efficient anyway. And we're at 45. So it's just not, it doesn't pay to add a whole bunch of more blades. For a helicopter, it does. Because now, if I want to lift a few tons, I'm paying for all this oil, but we're already about at the max. So I think 3 is where it's going to stay. But blade design itself, there's a lot going on, and because you want them to be high, to last a long time without maintenance. So right now, a lot of composite materials, fiberglass, different epoxies, carbon filaments, way to wind the blades, way to manufacture them with the twist that they need. And so there's a lot of work, and these are huge blades too. So we're talking about very large facilities to be able to wind the fiberglass. So there's research going in blade design and also in repairing blades. You know, the best way to do that, it's not so easy to repair fiberglass sometimes. Yes?
Yeah, I'd just be interested in knowing about the lifespan of some of these drivetrain components, and then also more generally, like, what the variable costs are associated with wind farms.
Yeah, the question was about the life, basically the life of the drivetrain, the transmissions. The 20 years is what they're designing for, okay? But you never know. And so a lot of the big wind turbines have what's called HUMS, Health Usage Monitoring Systems. They're a system that measures all the vibrations. And it's like your car. You're driving down the road in your car and it's shaking and rattling, and all of a sudden you feel a vibration you never felt before. A friend said, "What do you mean? Your car's shaking?" "No, this is new," or "This sound is new." So these health usage monitoring systems measure what's going on, and they say, "Wait a minute, there's a new vibration, a new noise we didn't hear before." And you can tell by the frequency, maybe it's right at a gear tooth passage, that maybe something's starting to crack in the transmission. And then it's a lot cheaper to stop, turn it off, go up and fix the transmission, because if the transmission breaks, I didn't bring it, there's a YouTube video of like one of these 5 megawatt machines with one of the blades flying off. You know, and then once it flies off, the whole center of gravity and the whole tower like came down. It wasn't the 5 megawatt, but like one of the 1.5. So, yeah, so that's the goal. A 20-year is a pretty good life for people would like to have with maintenance. I used to have to do, you know, some kind of regular maintenance on the machines to keep things lubricated. Electrical systems, and you're hoping by then the technology has gone so far you can do something new. Yes?
In terms of the installed costs,
Yeah.
the higher the hub height, the more you have to ballast the thing, and the larger the roads have to be to get into these rural areas. It begs the question about whether or not we should stop at a certain size, maybe even make towers that are guyable and hingeable at lower kW or megawatts,
Yep.
but at higher heights, so you get more shear.
Yeah, the question is, or the comment is, because you get higher the height, the more power you get out, but the more costly they are. And there's probably a trade-off. There was a paper one time I heard called "How Big is a Wind Turbine?" and trying to answer these kind of questions. The turbine we had out of Tyson was about 120-foot center, you know, and it was on a big pulley system. The whole tower came down into a cradle, right? Then you could work on the wind turbine down in the cradle and bring it up, but you get up to these. And so, yeah, it's going to be a trade-off. And the wind speed gets faster as you go up, and that's the benefit, but then the installed cost, the maintenance cost for these big cranes, yeah, there's a lot of, you know, for people in the economic field and for work and life cycle costs, you know, cradle to grave, how do you get rid of the thing when it's done, you know, in terms of getting environmental friendly. There's probably a lot of studies that could be done. There's also studies done on balancing solar and wind, because solar is more in the daytime and wind is more at the nighttime. You probably could get some synergy, you know, getting a fact where you have in fact, the big wind farms down in Texas, they're down in the desert, they're putting big solar panels in between the windmills. Say, we got the land. The land's free, right? I don't have to pay for land. Let's put these big solar panels up, and now in the daytime, maybe when the wind's down, you're getting more. So I think there's just no end to the kind of good studies people could do on how to optimize the energy output of a system. And that's really what you want to look at, a whole energy system for the country. Yes?
I want to ask whether biomimicry is used in the wind turbine design, because what I heard, if there are bumps on the wind turbine, the efficiency improves because you have copied that from a wave.
Yeah, this is a very interesting thing. The question is about bumps on blades. And people noticed that some of these whales had certain bumps on their skin. And they begin to, you know, why would that be? And they begin to do hydrodynamic studies and found there was an increased efficiency. For the wind turbines, it's not that big of an issue to put the bumps on because the drag is not that big. So it's kind of interesting. We are using the lift to really pull the wind turbine around, and that's the large force, and the drag is a smaller force. So there's not that much to be gained. Now, when you have I think there's probably a lot to be gained on passenger airliners and things like that, where you could actually put these bumps on the wings, you go up to higher angles of attack and not stall. But that's another issue then manufacturing. How do I manufacture these bumps? And even a golf ball, it's dimpled, right? And they did research, what's the optimum distribution of dimples, and the optimum is random. It's hard to get my mind wrapped about what that means, but the optimum could be random. But yeah, because it breaks up the flow and it keeps, it keeps the boundary layers from getting too thick, so it keeps, just keeps the drag down. But like I said, probably in wind turbines, the main research is not going to be on making the blades aerodynamically more efficient. Now there may be research, on how to throttle them better through a wide range of wind speeds. And this idea of yawing the wind turbine, so you're not just always frontal to the wind, and then when the wind gets so big you shut down, but slowly yawing out of the wind. And so you're always throttling and you're always getting the most power you can. And that was one of the things Kirko Nezzer was doing out of Tyson with our wind turbine. And there's some of the big ones in Europe are trying that now, trying to work on this idea of letting it be yawed. There's more vibrations then, more loads. So that's another trade-off. But in terms of how much power you can get out of the wind. I mean, even these wind turbines are so high, the wind speed is different at the top and the bottom. Right? Because the wind gets bigger as you go up, so the top is at a higher speed than the lower, so there's this gradient of wind speed across the wind turbine. That puts loads and forces on the wind turbines that they have to be accounted for and have to be designed for. Yes?
You talked about horizontal axis wind turbines, but can you highlight some of the main differences or trade-off between a horizontal and a vertical axis? And also, secondly, is there a movement towards going from huge wind turbines to maybe smaller ones for every household or something like that? What is the technology?
All right. There's two related questions. The one question was vertical axis versus horizontal. A vertical axis wind turbine has the blades up and down. So these wings are up and down and they're going around in a circle like this. The advantage is you don't have to point it at the wind. It doesn't matter what direction the wind's coming from. So there's no yaw mechanism. There's some of these, there's all different kinds. There's some on top of one of the Washoe buildings that's the corner of Delmar and Skinker. Some of these little white whirligigs things on the top. That's one version of that. Okay, to do. So that's the advantage. The disadvantage, though, is the efficiency of them, because the front blades stop the wind. And you can't, there's no, you're going to stop at a third, there's no use to stop it anymore, so the ones in the back can't do anything. So half the time the blades are useless. And then the ones in the front shed all this vorticity that shakes the ones in the back. So you get really big and they just don't work. But for small wind turbines, they do make sense. And I think there's a big market for small wind turbines to generate some. There's a wonderful book, The Boy Who Harnessed the Wind. This book. It's a true story about a kid in West Africa who couldn't afford to go to school because his family was so poor, and he just went to the library and read about engineering. And he ended up building a wind turbine for his village. With no machine tools, he went to the junkyard and picked up pieces. It generated electricity. He was charging their cell phones because they had to go to the next village and pay people to charge their radios, and he had put electricity in his village. He almost burned down his house till he discovered something called a circuit breaker, and he invented his own circuit breaker. But so there's a lot of applications, I think, around the world to pump water, to make electricity, okay, for small applications. Farms, and there's farms in Missouri where a person has a small wind turbine. But the problem is, of course, like if you're in Ladue, nobody's going to let you put a wind turbine on top of your roof, and it's even if you could, it's probably not going to make that much electricity. I mean, this is just we're webcasting, aren't we? Though. Well, this is just between us and the webcast. Probably those little whirligig turbines at the corner of Delmar and Skinker don't make enough electricity to light them up at night, right? Okay, so but they're pretty, and it's a statement. It's a statement, and sometimes like Alberici Construction has that big wind turbine out there, and that's just a statement, to say, hey, we care about energy, we care about wind, and that's good. But in terms of making a dent in how much energy is created. But the other question earlier, if you had enough of these things, maybe not, 100 kilowatt or 50 kilowatt, Yeah, there's probably an optimum size to get the most out of everything. And so, yeah, I think there's applications for smaller wind turbines, a lot of places to do a lot of things that could help a lot of people around the world. I think our Engineers Without Borders did a wind turbine project last year, I think, to try to get something like that. Yes?
I have heard oft repeated what appears to be now a fallacy, that the most efficient turbine is a one-bladed prop. What's the genesis of that totemization?
Yeah.
How can you destroy it? So I understand that.
Depends how you're going to define efficiency. Like these model airplane people with the rubber band model, some of them have one-bladed props. And if you said, I can only have so much length of blades, then your best thing would be take one blade as long as you could make it, because the swept area is very important. So in that case, if you're only allowed so many meters of blade, same with the airplane, make your wings as long as you can. I mean, but the thing is, you can't get into the hangar, or they hang, they bend down, they hit the ground. Like the U-2 wings actually did hit the ground, and the little wheels on. So yeah, if you're defining it that way, but if you say, I have a given area, and I want to get the most energy out of that area, then the most important thing is the solidity, which is what percentage of the area you're covering over in wings. And that optimum is about 0.05, 0.1. It's a thin wings, and you have less tip losses with more wings. And so if you look at the very highly efficient turbofans, turboprops NASA work on, they have many blades. They almost look like flippers on CC turtles or something go around, but you have a lot because you really want that. But yeah, it depends how you're defining this efficiency. Or same way, if you just have a given area and you want to pump as much air through it as you can, you fill it with blades. You overlap them. But if you want to have the least power to pump a certain amount of air, or you want to get the most power, then you make thin blades. So yeah, it just depends what it is you're optimizing. Yes?
I have another online question from Dr. Thomas, which is, how feasible and efficient will the lower speed wind turbines that are being developed today be?
Yeah, I think their efficiency, we're about to the max. Like you can never get more than 59%, and we're at 45 now. We'll get up, you can get up a little higher, maybe go, but that's probably the efficiency is probably as good as we're going to get. The real issue is going to be, finding the right places where you have steady wind speed and making them so they have a long lifetime, so you don't have to keep going back and doing a lot of maintenance on them, because it's life cycle cost. Here in the front, yeah.
I was wondering if you could talk about transmission of wind power. I know a lot of the wind resources are in rural areas.
Yeah.
What challenges are being faced
Yeah.
to the population centers?
The state of Texas is doing huge things on this, and they're building these huge infrastructure of power lines, of high-speed power lines, going from way southern Texas to Dallas and Fort Worth. They also have the problem, they have like 3 different electrical utility systems that aren't hooked together in Texas. We have this nationwide grid, but they have some that aren't on the grid at all, and trying to hook these all together. People are doing research, in superconductors and try to get that better, or ways to be more efficient, but as you go through, so you need wires that have less losses in transmission to do that, and that's one of the issues, trying to get you'd like to get this as close to where you could need it as possible, but in some places you can't, and so you're going to have to do it. So there may be other things I don't know about physics research, in terms of superconductors that aren't such low temperature, and things that could possibly get fewer losses as you go. But there's a lot of losses no matter how you look when you transport energy, right? So even your car doesn't use all that energy in that gasoline, and there's just the laws of thermodynamics operate against you. You can't get it all.
Time for one more question.
One more question. Okay, that's it.
So I have a comment and a question actually. Like this summer, your story came out from like a professor at Caltech who said, by using vertical axis wind turbines, you can increase the efficiency by like 10 times. Do you know anything about that?
No, but this happens all the time. McDonnell Douglas back in the 80s worked on what they called the gyro mill. It was a vertical axis machine, but instead of the blades just fixed pitch, they could articulate as they went around. And so they optimized them to get the perfect thing. And their first numbers came out and they were more efficient than 59%. They were thinking, wow, wow, wow. But then, began to look. Turns out you have to divide by how much energy is available. And that was the wind speed in the wind tunnel. Well, they had two different wind speed measurements in the wind tunnel. One was from the wind tunnel's own stuff, and they actually had a pitot tube sticking in it. The pitot tube had them like 51% efficient, and the little dial on the wind tunnel had them like 70% efficient. They averaged the two numbers, but it turns out it's not true. Yeah, I don't believe you'll ever get more than 59%. I think it's just a law of physics. Yeah.
My question was about like offshore wind.
Yeah.
I've seen like wind resource maps, and all of the really big resources are offshore, like 50 miles offshore. So why aren't we like doing a lot more offshore? Like especially since in the United States we have cities on the East Coast and West Coast, and like Chicago, like Michigan.
All right. I mean, there's two reasons. The question is, why aren't we doing more offshore? We should do more offshore. One reason, it's very expensive to build an offshore machine. It's not like here where you drive some trucks up and you clear a piece of land and you put it on there. You got ocean, you got to go down to the bottom, drive pilings, so that's an expensive thing. But also there's a lot of political fight against it, like we saw off the coast of Massachusetts, where people just don't want. They want to look out of their nice house on the ocean and see the ocean. They don't want to see a bunch of wind turbines out there, and they don't want seabirds to get killed. They're flying into the wind turbines. So I think it's part of each. It's economic, but it's also in terms of political as well. That was the last question, right? All right.
Well, if you have time to stick around for other questions.
One more. This is it. One more. All right, you can finish up then. Okay.
So
all right.
with offshore wind, do you think it could ever provide like a baseline instead of like, right now they talk about wind as like intermittent, so we have baseline coal and then wind is like, putting in the gas. Would offshore wind be like a baseline power source?
I mean, if you were offshore, right, you'd have wind all the time. Now still, you have a cut-in speed and a cut-out speed. It could be sometimes the winds are too big. I mean, you can't afford to build these wind turbines so that once a year you get all the power. You've got to somehow, you got to design for what's normal, and you have to be able, for hurricane or typhoon, to be able to stand against those. So, yeah. How much wind energy you could really get? I mean, people have done a calculation of all the wind energy and all the atmosphere of the whole Earth. How much at any one time? That's huge if you could get all of that. But you'd probably change the weather, right? If you slowed all that wind down. But if you look up into the jet stream, yes, and that's why these high tethered winds. There are the winds 100 miles an hour. And although the density is only half, you still got 500 times as much energy per square foot as you do here. So there's wind, and same with solar, right? If you could put a satellite out, look at all the solar you could collect, but how will you get that energy down to Earth and do it? So I think that's why there's going to be a lot of jobs for engineers in the 21st century, and maybe some of you all have the very creative ideas on how to do that. All right, thanks very much.